So welcome to the 35th lecture of this course. In the last lecture, I discussed the VI characteristics and the biasing of a diode with you. That is, the diode is either forward biased or reverse biased, and if the applied voltage is V and current flowing through this diode is suppose I. That is, suppose I say that if this diode, you have a diode and it is forward biased. I told you the condition for forward biased, the anode is at higher potential and cathode is at lower potential. Under this condition, suppose if I say that the applied voltage is V and the current flowing through this diode is suppose I. If this is the case, and of course the characteristics that I told you between this V and I is like this. And this is the bearer potential, or this is called the knee voltage. And when the diode is reverse biased means when anode is at lower potential. Generally we say that this anode is connected to negative terminal of the battery and cathode is connected to the positive terminal of the battery. Under this condition, no current flows in the external circuit. That is, this diode, it acts as an open circuit. It is acting simply as an open circuit, but a small leakage current flows. And after a certain stage, this V, after a certain stage, a breakdown occurs. That I told you, it is called the avalanche breakdown. Why? Because these electrons or these movable charges, they break the covalent bond and electron hole pairs are generated, which further multiplies, and an avalanche of charge is there, and very abruptly or abrupt rise in the current is there, and we should avoid this. So this is called the breakdown. This is called the knee voltage. I told you in the last lecture, this is called the knee voltage, and this voltage at which this breakdown occurs, the limiting value of this is called the breakdown voltage. So this is the characteristics. If the applied voltage is V and the current flowing this diode is I, so this is the characteristics that I discussed with you in the last lecture, and the characteristics is like this. Let me try it here. This current flowing here in the forward bias, it is this way, and here you have this leakage current, and after a certain point you have this breakdown voltage here. Now the current flowing, now I am interested in the diode current here, so I'll put the heading as the diode current equation. That is the current equation. Current equation means the current flowing through in a diode junction. And suppose I say if that this current is flowing is I. This current flowing through this diode is given by I is equal to I naught. I'll just define what this I naught and all this indicates. I naught into e to the power V upon neta Vt in suffix is t minus 1. This is the equation of this curve. It is exponential growth. As I told you, it is not a linear growth. It is a non-linear device. PN junction diode is a non-linear device. That is, the current does not increase linearly after this breakdown, after this built-in potential. Once it has overcome this built-in potential, the current increases exponentially. It increases exponentially, and this exponential growth of this current is given by this equation, where this I naught is called the reverse saturation current. It's called the reverse saturation current, or this is the current due to the minority charge carriers, we can say. I have discussed with you. This is this V is the applied voltage, of course. I is the current. I is the current flowing through the diode. V is the applied voltage. Let's talk about this neta. This neta is a constant. This neta is a constant, and its value is 1 for germanium. If the initial semiconductor that was taken, if it was germanium, then the value of this neta is 1, and it is equal to 2 for silicon. It is 2 for silicon. This Vt is called the volt equivalent of temperature. This is called the voltage equivalent of temperature. That is, it is a voltage temperature dependent voltage, and that is given by Kt upon Q. We have done this term, if you remember, we have already done this term Vt, Kt upon Q while dealing with Einstein equation. dN upon mu n is equal to dP upon mu p is equal to Kt upon Q. If you remember, we have done this thing, Einstein equation, while dealing with drift current and diffusion current. I have done this term already with you. So it is Kt upon Q, that is where K is the Boltzmann constant. Let's define this once again. This K is the Boltzmann constant. This is called the Boltzmann constant, and the value of this, you all know it is, I think it is 1.38 into 10 to the power minus 23 joule per coulomb. Of course, Q is the charge of an electron, and it is equal to 1.6 into 10 to the power minus 19 coulomb, and this T is the temperature in Kelvin. This is the temperature in Kelvin. Or if I substitute the value of this K and Q here, I can say that this Vt is approximately equal to, I think, 11,600. I'm sorry, it is T upon 11,600, or even at room temperature. At room temperature, that is, if I substitute this T is equal to 300 Kelvin, that is when T is equal to 300 Kelvin, that is 27 degrees centigrade, 27 plus 273 into 300 Kelvin. So this Vt is approximately equal to 26 millivolt. This is equal to 26 millivolt. So this is the current flowing through diode. That is, if this diode is applied, if a forward voltage of V is applied through this, and the current flowing here is I, then this is given by I is equal to I naught. Of course, this I naught is the current due to minority charge carriers, V upon neta Vt minus 1. Will not go through the derivation of that, it is not part of your syllabus. So, but the equation you must know, this is the current flowing through any diode when a voltage V is applied, a battery of voltage V is applied, it's a forward voltage, and this current is given by this particular equation. I'll deal with a very small numerical based on this. Let's do a problem. Just simply formula based problem I'll take. So suppose that a problem is given to you. I'll take a very simple problem. I'll write the problem also. The problem says that a germanium diode carries a current. I'm writing a problem. A germanium diode carries a current of 1 milliampere at room temperature, of 1 milliampere at room temperature. That is, it is given that this current is 1 milliampere at room temperature when a forward bias, of say 0.15 volt is applied. And it simply says that determine the reverse saturation current. Reverse saturation current. A very basic problem, simply based on the formula that I have just discussed. Now look at the solution. It says that there is a diode which carries a current of 1 milliampere. Look at this. I draw this. It's a diode here. And a current of 1 milliampere is flowing. The current flowing in this diode is 1 milliampere. That is, this I is given to you. What is given to you? This I is 1 milliampere. This is 1 milliampere. When a forward bias of 0.15 volt, if you say what is applied here, it is 0.15 volt. So this voltage, applied voltage V is given to you, that is 0.15 volt from here. and it says that it is at room temperature. Room temperature means T is 300 Kelvin or 27 degrees centigrade. So it is clear. And since it is a germanium diode, at the same time that this is the material is germanium. Now see, I have a formula. Look at this. Since I know that the current flowing through this, and what is asked, determine the reverse saturation current, that is I naught I have to find. Now as per formula, I is equal to I naught into e to the power V upon neta Vt minus 1. I apply this. In this I have to find the value of I naught. I naught will be equal to this factor. Now what is this? Look at the problem. One more thing that I can deduce from here, since it is a germanium diode, since it is a germanium diode, this implies that what is the value of neta from here? The value of neta will be 1. I have just discussed that value of neta is 1 for germanium and 2 for silicon. Had it been silicon, had it been given that it would have been silicon, then the value of neta would have been 2. Now, so it is equal to this much. And Vt, what is the value of Vt? At room temperature, Vt is equal to 26 millivolt. Since it is saying that it is at room temperature, so directly you have this Vt is 26 millivolt, and I can say it is 26 into 10 to the power minus 3 volt. I simply substitute these values here. I is equal to 1 milliampere. 1 into 10 to the power minus 3 is equal to I naught into e to the power V. This V is 0.15 upon neta is 1. Vt is 26 into 10 to the power minus 3. This factor minus 1. And if you just this upon I0 will be this upon this factor, and if you do the calculations from here, you will get the value of I naught is equal to, as per my calculation, it is approximately 2.48 microampere. 2.48 microampere, that is 2.48 into 10 to the power minus 6 ampere. So this is the current flowing through this diode I hope that this is clear to you. Let's come to one more next topic that I'll discuss now, is the zener breakdown. Zener breakdown. What do you mean by the zener breakdown and a zener diode? Before coming to this, let's discuss what do you mean by a zener diode first. Next article. Now, before coming to zener diode, let me discuss one more type of diode that you have is called a zener diode. Zener diode. This comes under a category that is called breakdown diodes. Now, we have discussed the PN junction diode here. A PN junction diode is here. Let's talk a simple PN junction diode is here. The symbol of this PN junction diode is this, and there's a PN junction. Now suppose this P side and this is N layer of this. If I reverse bias this, if I reverse bias means P is connected to negative and N is connected to positive, that is P is at lower potential and N is at higher potential. I told you in this that what happens if I keep on increasing this voltage, the reverse voltage, a leakage current will flow. Of course, a stage will come that the charge particles either on N side or on P layer, they break the covalent bond. When they break the covalent bond, electron hole pair is generated, and further these generated electron hole pair, they further break the covalent bond, and few more electron hole pairs are generated, and there is an avalanche of this electron hole pair and a very high current flows, with which the junction temperature increases. The temperature will increase and this may damage the diode. This breakdown is called avalanche breakdown. This breakdown is called the avalanche breakdown. Now, what Zener suggested, that although this reverse bias after a certain stage it is a harmful one, but let's make it useful. So what Zener suggested, he suggested a different same type of diode, but Zener diode is nothing. Zener diode is simply, when I talk about a Zener diode, A zener diode is nothing, it is a heavily doped PN junction diode. What Zener suggested that while constructing this diode, while making this P type or N type, this is made P type or N type, a semiconductor is made P type or N type by adding the acceptor impurity here and the donor impurity here. Now what Zener suggested that dope it at a very high level, high concentration here, and a very high concentration of this side also. So it is a heavily doped, means approximately it is 1 lakh times more than the normal diode, normal PN junction diode, a very heavily doped PN junction diode. Now what will happen that when this is a heavily doped PN junction, what will happen? A depletion layer will be formed here, no doubt. A depletion layer is formed here. But the width of this depletion layer is very less, is very small, this width, L, or I say let's represent this by W. So when this is heavily doped, this implies that the width of depletion layer, W, is the width of depletion layer is low. Now what will happen that if I apply electric field here, that is when I reverse bias this, a high electric field will be generated, V by L. Electric field is V by L. If this L is low, this E is very high. So what will happen that this breakdown will occur very fast, very quickly, and this will not damage the diode. In the previous case, in case of avalanche breakdown, it was because the kinetic energy of these charged particles, they increased and electron hole pairs were generated. On the other hand, this breakdown is due to this heavy electric field. So this type of breakdown is called a Zener breakdown, and it is used in Zener diode. So Zener breakdowns occurs in Zener diode. We'll discuss this Zener diode and its application. It is very useful, this Zener diode. Zener diode is what? It is heavily doped diode. Heavily doped PN junction. So, and the symbol of this Zener diode, if I draw the symbol of this Zener diode, it is ordinary diode here. Simple diode is like this, and I make a shape of Z here. This is called a Zener diode. When I reverse bias this, look at the characteristics of this. The characteristic of this is like this. Of course, in forward characteristic it is same, V, and this is applied voltage, and this is the Zener diode, sharp, and this voltage at which it occurs, this is called the Zener voltage, which is represented by Vz. This Vz is called the Zener voltage. This Vz is called the Zener breakdown, or this is called the Zener voltage, or the breakdown voltage of this. On the other hand, the previous one was let me show it here only. This, on the other hand, this one is your avalanche breakdown. So this green one is representing the Zener breakdown. Let me show this with green pen. This is representing Zener breakdown. I am writing BD. BD means breakdown. And this blue one is the avalanche breakdown. Many times it is asked the difference between avalanche breakdown. So this is Zener breakdown and this is avalanche breakdown. So if I say what is the basic difference between this avalanche and Zener, the basic difference between the avalanche breakdown and Zener breakdown. Avalanche breakdown is due to increase of kinetic energy of the charged particles. On the other hand, this is due to applied electric field. High electric field. Why? This is V by L, because electric F-I-E-L-D. It is electric field. I hope that this is clear to you. Electric field means this width E is V by L. This length is very less. Depletion width is very less. So it is high electric field. It is large electric field. This occurs early, this occurs very late. Alright, so this avalanche is harmful. Remember that after a certain stage. And this is useful. Mainly these zener diodes are used in regulators. We'll come to this part in detail. So I'll stop it here. So this is the basic difference between a zener. What is zener diode? First of all, zener diode is simply a heavily doped PN junction diode, and the breakdown which occurs due to high electric field because of the small or very less depletion width. A high electric field is developed, and from there a breakdown occurs that is called a zener breakdown at a very low voltage. On the other hand, this avalanche breakdowns, it occurs at a very high voltage, which increases the junction temperature and which may damage the diode. And this is useful. This zener diode is mainly used in regulators. So I'll stop it here and I'll continue with the next topic in the next lecture. Thank you for the time being.